So normally you receive the mail for the bus, for the social event. Now the bus is a bit too far away from most of your hotel. So we asked the local organizer if they can propose another place. And as soon as the bus driver said that this is okay, we will notify you. So maybe it will not be close to here, but close to another hotel that is closer to the Barry Center of all the hotels, you know?
Yes, okay. All right. Now we can start. All right. So, as you've already heard, I'm McClure, and you heard about some of the things I do with the Gemstone product line and Gemtalk systems this morning. Today I'm going to talk about threads and going beyond them. But before we do that, I would like to ask you who in the audience might know what this little drawing represents. Just as a clue, it's not some kind of weird UML diagram or anything. It's actually simplified, but an actual representational drawing is what it's meant to be. Well, okay. It's a unicorn at a birthday party. And I would like to thank my wife, Nancy, who came up with this and actually won a contest with that drawing at one point. And the reason I bring that up today is that this summer I celebrate a Smalltalk birthday, and I want to, have this be my birthday party in part and to share it all with you. 30 years ago this summer, I used Smalltalk for the first time, and also had an event that was a bit unusual in that it was a Smalltalk user group meeting in which no one there had ever used Smalltalk. Possibly the only time this has ever happened anywhere. And the way this happened was, in 1985, it was not all that easy to get Smalltalk. You had to spend a lot of money or know somebody really well to get Smalltalk in those days. I'd been interested in Smalltalk since I first heard about it in 1975, but hadn't actually managed to run it. So when Apple announced that they were going to release Apple Smalltalk for just $50 to send you the stack of diskettes that it came on, I immediately ordered it and then immediately organized a user group. And the problem was that the date that we had picked for the first meeting had not yet arrived. So I think 6 people showed up for this meeting, and none of us had ever used Smalltalk, but we were all interested in it. And so we talked about Smalltalk that night, and then a few days later, the Smalltalk arrived, and I started playing with it. So by next month's meeting, I was the expert. I knew so much more than they did because they'd never used it at all, and I knew very little, but more than they did. So 30 years later, let's move on to 2015 and to things that might affect the future of Smalltalk. So if we want to go beyond threads, first let's take a look at what threads are and get an idea of why we might want to leave them behind. So threads, and we'll back even farther off at first to the sequential model of computing, which is where computing began and where it still mostly is. Sequential model of computing is very simple. You write a list of instructions and the computer does things one after the other. And you can add in that you have branching and call return. You can have conditionals that go one way or the other. You can call subroutines and return, so you get some nice modularity that way. but still it's basically a sequential model, list of instructions the computer follows it in order. Now, the drawback with the sequential model is it only does one thing at a time, and sometimes you want to do more than one thing at a time. For instance, you might have a web server, and while it's actually preparing the response to one request, you might want to be able to take another request, or at least know you have another request coming in. So what we end up with in Smalltalk and many other environments is what's called the shared state thread model. And in this model, you have many threads of execution, each one of which is one of these sequential executions. But they're sharing the same memory, or in an object system, the object space, that state is shared between them. So they all have access to be able to send messages to the same objects, and so on. And they're called processes in Smalltalk. That's somewhat obsolete terminology now. Back in the 70s, when that terminology was being come up with, the term process had not acquired its current meaning of independent things that have a separate memory space that is not shared. Today we usually use the words thread. I will just refer to this as threads today. So it has some advantages. You can do more than one thing at once, or some definition of at once, depending on how many CPUs you've got and how many machines it's distributed over. And you can program it using more or less the same old sequential model that you're used to programming in, that we've been programming in since the 1940s, really. But there's also some drawbacks to threads. You program sequentially, but you basically execute randomly. Okay, randomly is a little bit of an overstatement. But nevertheless, each thread executes its operations in order, but the way that threads operate relative to each other, the number of possible ways that the threads can line up and order their operations is near infinite, because almost anything by default is allowed. So what you end up with is what's called race conditions, which is basically that if that you have certain points where if this thing happens before this thing in a different thread, then you get one answer from your program. But if it happens the other way, then you get a different answer. Sometimes that answer is program crashing. In any case, what you want is a deterministic answer, and in a lot of cases it is. What you do want is a deterministic answer from your program. Then a race condition is a bad thing. So what you end up doing is you end up putting restrictions on how the threads can interweave with each other. And you do that by such things as, well, you can do it somewhat with thread priorities, but most you do it with some kind of blocks. In Smalltalk, we use semaphores because in the 70s, semaphores were the hot new concurrency tool, and so, of course, that's what Smalltalk used and still uses. But if you overuse the locks, then you end up with the potential for deadlock, where you have a circular dependency between locks, and your threads that are engaged in deadlock all come to a halt and have to start up again. So you end up with too few locks, you get race conditions. Too many locks, you get deadlock, or locks in exactly the right place, and everything just works. But in order to do that, you basically have to understand the entire system every time you look at your code in order to get it actually correct. Because in a sequential model, you normally, in many cases, you just have to look at the code right around the place you're looking, because you can see kind of where you're coming from and where you're going. But in a system that's multi-threaded, then you have to think about every possible instruction in every possible thread that is executing at the same time as this one line of code that you're looking at to see whether or not it's correct. And no one can hold that in their head. And so the problem is that you have to, another problem is that you can't really test for this very effectively, because the number of possible ways for this to interact is so great that running test suites only exercises actually a very small number of the possible ways these interact. And you see this a lot in, like you come up with a new generation of hardware and you suddenly run this thing and it nearly leaves a way it's never done before, and you suddenly get a deadlock, or you suddenly get a race condition that you've never seen before, even though you've been testing the heck out of the thing. So in case you haven't gotten the idea, I'm trying to tell you that threads are bad. And I'm not the first person to say this, and I won't be the last person to say this. There's quite a history of people saying that threads are not a good idea. Here's a slide from a presentation, an invited talk at the Usenex conference in 1995 by one called "Why Threads Are a Bad Idea," in most cases. And in here, there's a continuum of programmers, from casual programmers up to wizards, and Visual Basic programmers go all the way down. Anyway, thread programmers are the red arrow way over on the right. So you have to be a wizard to be a thread programmer, he says. And this is too hard for most programmers to use, and even for experts, it's painful. And this is certainly true. 10 years ago, there's a paper, The Problem with Threads, by Edward Lee, who was the associate chair of the computer science department at UC Berkeley. And he says a variety of things. I'm going to quote from his abstract, and I put this on the notes, and I thought that my presenters council was going to tell me what I actually wanted to say, but it doesn't. Threads seem to be a small step from sequential computation. In fact, they represent a huge step. They discard the most essential and appealing properties of sequential computation: understandability, predictability, and determinism. Threads are wildly non-deterministic, and the job of the programmer becomes one of pruning that non-determinism. Although many research techniques improve this model by offering more effective pruning, I argue this is approaching the problem backwards. Rather than pruning non-determinism, we should build from essentially deterministic composable components. Non-determinism should be explicitly and judiciously introduced where needed rather than removed when not needed. So that's his basic thesis, and it's an interesting idea and one that has borne fruit elsewhere. And going beyond threads today, I want to take a look at what has the package of ideas that are in the E language. Who here is familiar with E? Yes, good, a few. Have you actually used it? Have you written programs in E? No. Not me neither. So you won't be able to correct me if I get stuff wrong. I told you would. But I've been reading a lot about E, and it's an interesting package of ideas. Now, the ideas I'm going to talk about here are not new. E itself is about 15 years old, and it drew ideas from many things before it, notably the after model. Even the idea of taking some of the ideas from E and bringing them into Smalltalk, this idea is not new. There were a number of projects about 10 years ago that were bringing some E ideas into Smalltalk, most notably Croquet, for instance. There were a few other projects. As far as I know, none of those projects are active today. So I thought I'd bring this up again, because I had not really noticed them at the time. And I think it's kind of interesting. So what is the E language about? Most of the information that I'm going to present today I got from Mark Millar's doctoral thesis, which was on the E language. He was one of the original developers and probably the chief person today. And in the abstract of his thesis, he says this: when separately written, I can't read it this time, I'm sorry, I'm going to read it out of here. When separately written programs are composed so that they may cooperate, they may instead destructively interfere in unanticipated ways. These hazards limit the scale and functionality of the software systems we can effectively, successfully compose. So the problem statement he's giving is that you want to be able to take pieces of code, components that are written by separate teams or people, and put them together and actually have them work. Now, this is a well-known desire in computer science. Great progress on the composition problem has been made within the object paradigm, chiefly in the context of sequential single machine programming among benign components. All right, so he says, objects are great, but basically they're great when you only have one thread and when your components are not malicious. So what he wants to do with E is to extend the success of objects to support robust composition of concurrent and potentially malicious components distributed over potentially malicious machines. So he's also introducing with E distribution, as well as concurrency. So So E is basically about objects, composing components, dealing with concurrency, dealing with distribution, dealing with security. E is actually known more for its security properties than for its concurrency properties. But like the picture of the unicorn, I'm going to zoom in on just the concurrency part for today because, yeah, no time. Okay, so the first concept of E is the VAT. Now the VAT is E divides the world into VATs. And a VAT is every object belongs to a single VAT. So basically the world is partitioned into groups of objects, each living in, each group living in its own VAT. The VAT is roughly analogous to an operating system process. So as an operating system process has its own memory space, a VAT has its own object space, and a VAT has a single thread of execution. And everything within a VAT tends to look a lot like a single-threaded Smalltalk program, really. But in E, there's two kinds of message sends. There's the immediate message send, which is the thing that we're all familiar with in Smalltalk. You send a message, you wait until you get a response, and you continue your method. And there's also an eventual message send. And the eventual message send is one that is, you send it, and the sending method doesn't wait for a response, it just continues on. And that message send is queued for execution later. Here's a diagram from Mark's thesis of what a VAT looks like. So you have your heap of objects, and you have, like you would in any Smalltalk virtual machine, and you have a stack. The stack, because you only have one thread, there's only one stack. But then you also have this queue here, and that's the queue of undelivered eventual sent messages. So, and what happens is, when you first start up, you take a message off of that head of that queue, and you deliver it to the object that it is addressed to, and then you let that run, and it does its normal calls on the stack. And when it returns from that first message send, that is called a turn, that whole sequence. And then it takes the next turn by picking the next thing off the queue, delivering that message, executing that, and that returns. That's the end of that. So that's reasonably straightforward. Okay. And there's also two kinds of object reference within PE. There's but let's take a look at what an object reference is in Smalltalk, just to give us a frame of thinking about this. So an object reference is a thing in Smalltalk that we use all the time, but we don't really maybe think about all that often because it's just there. But there's two things you can do with an object reference. You can assign it to a variable. In fact, that's all variables do, is they hold object references. Every variable always holds an object reference. And then you can use that object reference to send a message to an object. In fact, you can't send a message to an object unless you have an object reference. So since assigning to a variable is really just sort of saving it for later use, the sending of the message is the important part. So I'm going to define an object reference as a channel through which you can send a message. And that is true in Smalltalk, and it's also true in E, and especially in E, where things are distributed. Thinking of an object reference as a channel through which you can send messages is a helpful way to think of it. So back to our two kinds of object reference in E. There's the near reference. This is the one that we're used to in Smalltalk. It's only good within the single VAT. And then there's the eventual object reference. And this object reference type can refer to an object in any VAT, anywhere in the world that your entire system knows about. So the differences between them are in what you can do with them. The near one, you can do an immediate send, like you've seen. So that's the traditional Smalltalk model, the immediate send. Send a message that then you wait, it gets delivered immediately, and then you wait for a response. And the eventual send, where you continue on immediately, but that message gets queued for later delivery. The eventual reference, you can only send do eventual sends through. If you try to do an immediate send through an eventual reference, you get an error. So here's a diagram of that actually happening. Here we have an example here of an account of some sort that is being monitored by a listener object that is a spreadsheet that wants to display its values and update its values when balance of the account changes. So we have a manager object who immediately sends an update of balance to the balance object. And then it updates its value, but then it has a number of listeners, in this case only one. So it eventually sends a message to a listener which is living in another vat. And that queues it here on queue. And then eventually, after some number of turns of execution in that vat, then that message is then sent and delivered to the spreadsheet, which then updates its display. So that's pretty much the way things work in general. Now, there are several parts to any message. A message always has a receiver, a message always has a selector, and a message always has arguments. 0 is one of the possible number of arguments, but 0 or more. So the way we handle arguments are that if the arguments, when you sent the message, were a near reference into your own vat, then when you send it across to a different vat, then it has to become an eventual reference to that object in the vat where you're coming from. So, because you can't have a near reference, it goes across vats. And there's an exception to that rule. You don't always get things back, and that is for a thing called data objects. And a data object is any object that is transitively immutable. So, for instance, a small integer is a data object. A symbol is a data object. An immutable structure, like a date that contains several integers, if the date itself was immutable and the integers were all immutable, that would be a data object. Now, whenever you pass one of those, then it's just copied across because the object can't change. So any copy of that object is equivalent. So they're just passed by being copied across the wire. And then the receiver sees that as a near reference in the receiving that. Okay. So I'm about to dive another level deeper, so I thought I'd stop at this point and make sure everybody's kind of with me so far. Any questions about what I've said so far? All right. And let's go on. Okay. As we saw before, an immediate send waits for a response before it returns. But an eventual send returns immediately to the sending method, and the sending method continues. But that leaves the question unanswered. What does it return? Because the message that it sent hasn't executed yet. So what you actually get back is you get a promise for the result. And the promise is an object which is an eventual reference to the result of your message sent. And the way that this comes about is that when every promise is created, there is also created a resolver for that promise. And then it is sent with the message, or actually what is actually sent across the wire or across between vats is instructions for creating the promise on the other side, because the promise is local, or the resolver is local. The promise stays on the sending side. The resolver is created on the receiving side of the message. So there are two different vats. The resolver has a reference, an eventual reference back to the promise, so that when the method completes, it can tell the promise what its resolution was. So it can pass back knowledge of the result object that way. And since a promise is an eventual reference, you have an eventual reference to it in your sending method, then you can send messages to it at any time. And you can send messages before it's resolved, and any messages sent to a promise before it is resolved are queued up in a FIFO queue in that promise. At the time that it's resolved, then those messages all get sent to the resolution of the promise. And once the promise is resolved, it is completely equivalent to the resolution itself. For example, if the result of your message sent was a data object, then the promise actually becomes a near reference to the data object, and you can use it just like you could if you had it all along. So in a distributed system, one of the problems that you have is network latency. And we see this in the classic gen builder for Smalltalk architecture and the Gemstone product lines. We have a distributed system between a VisualWorks or VA Smalltalk client and a Gemstone server. And we have forwarder objects that when you send a message to a forwarder on the client, it will forward that message onto the server object, and what that sends back could be a forwarder object on the client side as well. And in that case, something simple like this, testing some object. This is just a bogus example, but you would send the work queue object, which is a forwarder that you have in your hand. You send it the remove first method, that's sent across the wire. You wait for a response to come back. That's made into a forwarder. You send it process, that's sent across the wire. You wait for a response that comes back. You get the forwarder. You send it equals, and you make all these network round trips through fairly simple code. Some of the newer things in GBS have made this a little less painful, but there's still, you have to make more complicated code in order to avoid network round trips. Whereas with E's scheme, you can do the same thing and avoid the network round trips. You say, you have an eventual reference to work queue, you send it the remove first message, that sends an eventual send across to another VAT, and gives you back a promise immediately. You send that promise process, that does another eventual send, gives you back another promise for the result of that. You send that equals, and it makes another eventual send and gives you back a promise for that. But you're not waiting for the response, so these message sends are simply streamed across the wire one after the other without waiting for a response. So you cut down on your network latency big time. And this is, for a distributed system, this is a fairly big deal because machines keep getting faster, but the speed of light stubbornly refuses to follow Moore's law. But things don't always go the way we want them to. So you can have exceptions. So within a turn inside of a VAT, exceptions are handled pretty much like they are in Smalltalk. You toss an exception up the stack and find it in a handler and deal with it. But if you reach the top of the stack in one VAT in a turn, and you haven't found a handler, then what do you do with that exception? Because the sender of that message is off in some other VAT somewhere, and they've gone on, and they've sent messages to the promise, and they've done all this stuff. So what do? Well, what you end up doing is that the promise ends up resolving to what's called a broken reference. And any message sent to a broken reference then signals that exception that broke the reference in the local stack of the sender. So you do indirectly, once somebody actually tries to use that promise, then they will actually get the exception back in their place. So there is a means of handling that. There's also, promises are also broken when you get, for instance, a network partition and VATs become unreachable and that sort of thing, which can happen when you have a distributed system. So that's most of the really, really basic part of E. I'll just talk about a couple of odds and ends that round things out a bit. There's also a WinCash type of construct that you can use to set up a handler for what happens when a particular promise is resolved. And the when part is if it resolves to an object reference, and the catch part is executed if it becomes a broken reference. You can use this to implement things like multi-way joins of eventual sends, so that you don't proceed until more than one of your eventual sends have actually completed and resolved themselves, and all resolve themselves to a value, and you know they're not broken. There's, in order to create a fully complete data flow type vocabulary, you need that kind of thing. There's also a particular guaranteed order of delivery of some of these messages, which I don't have time to go into today. So that's kind of the basics of E and its concurrency properties anyway. So then we have the question, well, is this a good idea? It's an idea, certainly, but is it a good idea? Well, it does have some advantages. Because there isn't any shared state, all the state is held in VATs, and each VAT is single-threaded. You really eliminate all of the classical race conditions. Because there are no locks,